Before we move on to other aspects of graphing and different things besides graphing lines, I want to talk about a little bit of vocabulary that you're going to see. The first thing that I want to talk about is a relation, which is just a set of ordered pairs. And that just means any grouping of x and y values. It doesn't matter how they're represented, any group of ordered pairs is considered a relation. We'll see a set of ordered pairs written usually as, that's our grouping symbol for the set, and then an ordered pair with an x and a y. Just make up some numbers here. There is a relation. It's a set of 3 ordered pairs. 1, 2, 3 ordered pairs. Each one has its own x and y, and they're grouped together by the braces here. Another way we may see a relation written is as an equation, and they could be of any form. This is just one example. Y equals 2x plus 1, that's a relation. Remember, and the solutions to an equation are all ordered pairs that make this true. Well, so that is a set of ordered pairs that make that equation true. Another example would be a graph. If I were to graph that equation, since all equations make some kind of graph, the graph itself is a set of ordered pairs. Every pair on the line is a solution to the equation, so every ordered pair then forms a relation. That line forms a relation. The domain of a relation is just all the first coordinates. In other words, all possible x values. So let's take a look at this first one. The domain is just the set of all my x's. So for instance, in this first relation I created where I had 3 separate ordered pairs, the domain would be 3, 0, and 2, since those are my 3 different x values, 3, 0, and 2. The range is all the second coordinates, or all the possible y values. So for our range, we actually have 2 distinct y's. We have a 2 in the first ordered pair, and then both my second ordered pairs have a 1 as the y. And since 1 is listed twice, I don't have to list it twice in my range. I only list in my domain and range distinct values, values that are different from other values. So if I have any repeats, I only have to list them once. We're also going to look, as we go on, domain and range of equations and graphs, and we'll get to some examples of that after we look at another definition. And the definition in this case is the definition of a function. A function is a relation in which every element of the domain is paired with exactly one element of the range. In other words, each first element has exactly one second element. That's all a function is. If I have a first element listed, if I have an x value listed, its corresponding y value can't be different. Here I have an x value of 2 and a y value of 0. Here I have an x value of 2 and a y value of 1. Since I have the same x that coincides with 2 different y's, this relation is not a function. Function notation, we see when we're writing the equations of functions, it's read y equals f of x, not f times x. Many people make that mistake, but that's an important one to remember. This does not mean f times x. So when we see function notation, we usually see it written as f of x, which corresponds to y, and then I can use the same equation I had before. These are equivalent ways of writing an equation that is a relation. This one just happens to be in function notation, which indicates that our relation is also a function. Function notation is useful because it tells us what number we plugged in for x. Well, in this case 2. So function notation is nice because we can find a y value and still keep track of what x we plugged in to begin with. So this is read f of 2 equals 5. So for the function I created, I plugged in 2 for the x, which meant plug 2 in for the x on the other side and work it out. Now that corresponds to the ordered pair 2 plugged in for x. I got 5 as my y value. Again, these two things are also interchangeable. Function notation for an ordered pair and ordered pair notation. So when we are trying to determine whether or not a relation is a function, we could run into one of three possibilities. Our relation could be written as a set of ordered pairs, in which case we just look at each ordered pair and make sure that if the number that appears as the first element happens more than once, its second elements are not different. If the second elements are different, then it's not a function. And that's an odd description, I know, but we'll see what that means when we get into some examples. When we're looking at a relation written as an equation, can we solve for y without taking a square root is the most common way of knowing that it's not a function. If we take a square root, there are other instances where we would say it's not a function, but square root's the most common and the only one you'll see in this class. So if we can solve for y without taking a square root, if the answer to that is yes, then it is a function. Otherwise, it's not a function. Graphs are the easiest way of telling whether something is a function. If it passes the vertical line test, then it is a function. And the vertical line test is described here. When we graph a relation on the Cartesian plane, which just means the xy plane, the relation is a function if and only if no vertical line passes through the graph more than once. And for instance, if I had the following graph, and it was a graph of a circle, let's say. If I draw a vertical line through that circle, I hit this graph more than once. I hit it there and there. That means this is not a function. On the other hand, say I have the graph of a line. Anywhere I draw a vertical line, I'm only going to hit one time. As long as that is true, I hit 1 or 0 times with every single vertical line. This is a function. So we're going to do some examples now of relations written in different ways, and we're going to determine the domain and range and then state whether it's a function. So for our first example, we have an oval drawn on the xy plane. Anytime I'm looking at a graph, it's easiest just to do the vertical line test. So if I draw a vertical line anywhere, just say right through the middle of it, I hit 2 times. More than once means not a function. So I know the answer to the second part of this question already. This is not a function. I still, however, have to determine the domain and the range. Well, remember, the domain is all possible x values. Well, x is run left to right, so here's the smallest x value, -3. 1, 2, 3 to the left. here's the farthest x value to the right, positive 1. So my domain then, and this is called interval notation for those of you who haven't been exposed to this before. My domain is every x between -3 and +1. I write it in brackets because I actually hit the values of -3 and +1. Had I not actually touched -3, we would have used parentheses. And we'll see some examples of that as we go throughout the course. But just bear in mind that bracket means I hit that point. Parenthesis means I did not. The range is all possible y values, and I always go from bottom to top. So my lowest y is right here. The y value is -1 because it's down 1 from the middle. The biggest y is all the way up top, which is +1 as the y value. So my range runs from -1 to +1 and includes the endpoints. We have another graph. We're going to describe the domain and range and then determine whether it's a function. The domain of this function, remember I'm looking for all possible x values. Well, my graph has this arrow going to the left. It's going down and to the left, but it's going to the left. So that means that my graph continues on to the left forever. So I have no minimal x value. It just keeps going left forever. So to write that, I say I'm going to -infinity. There is no smallest x. It just continues on forever. On the right hand side, I have another arrow. And while it is also pointing down, it is pointing to the right forever, meaning this graph extends to the right, meaning there's no upper bound as far right as I can go. So I'm going to +infinity since I'm going to infinity in the positive direction. The range is similar. Remember, range is y values. I always start with the bottom because I'm always going to go smallest to biggest on these intervals. And the smaller y values are down. Now both of these arrows point down, indicating there is no minimal value for the y. The graph goes down forever, so my range goes down forever. There's no limit as to how low my y gets. But there is an upper y value. My graph never gets any higher than this point right there. Well, the y value there is 1. So my range goes from -infinity to 1. Since my graph hits the y value of 1, I use a bracket on that end. I always use parentheses when dealing with infinities. That's because technically speaking you can never reach infinity, and that's what the parenthesis means. I never actually reach that value. Now, is this relation a function? We're going to do the vertical line test. If I draw a vertical line here, I hit once. Here, I hit once. Here, I hit once. I'm always only hitting this graph once, so yes, this is a function. Move on to another example. This time we're given an equation. We're going to sketch the graph and then determine the domain and range. So we're going back to graphing, which we touched on last lesson. Y equals 3. Well, remember, to graph a line, I need 2 points. And each point has an X and a Y. Now the neat thing about this is there are no X's, there's just a Y. Y equals -3. So no matter what I pick for my X, my y value is set at -3, so I can pick anything I want for my x, say 0 and 1. So I'm going to go over 0, down 3, put a point. I'm going to go over 1, down 3, put a point, and we see that these 2 points make a line that just goes horizontally left to right forever in both directions. And we know that's the case because in the last lesson we learned that horizontal lines are the function or of the format y equals just a number, and this equation follows that format. So the domain and range for this. Well, my graph, again, a line goes forever in both directions, and this line is flat, but it goes left forever and it goes right forever, never skipping any possible x values. So I know my domain is going to be -infinity to infinity. Now, this graph does not go up or down at all. It stays at one value. Well, my equation tells me what all possible y values I have. I just have one y value, so the range in this case is just -3. Since it's a single number, a lot of times you'll see it put in these braces, the same thing they use to group the ordered pairs and relations. So here we see an example of a graph that while it has an infinite domain, its range is just one number. It's just a flat line that never takes on any other y values besides -3. Take a look at another graph. We're going to find the domain and range. The domain is the x values. And I'm starting here and touching that point. So I have a number to start at. It is -1, 2, 3, 4. So my domain starts at -4, goes all the way around the circle to this side, which is +4, that it also hits. The range is all possible y values starting from the bottom and going up. So we start at the bottom, -4. Goes all the way around the circle to the top to +4. Out of curiosity, it didn't ask, but we'll check, is this a function? Well, if I draw a vertical line, boom, boom, I hit twice, so we can say, even though it didn't ask, that this is not a function. We're going to sketch the graph of x equals a number. Now we can do that by either making a table of values, like we usually do when graphing, or we can recognize that this is a special format. When x equals a number, I know it's going to be a vertical line through that number. Well, if x equals -4, there's -4. Vertical lines go straight up and down. So I just draw a vertical line through that. Similarly, I could have said, well, my x is set at -4, but there's no y in that equation, so I can make y whatever I want, and then plotted those 2 points and came up with the exact same line. Either way is a legitimate way of graphing them. It's whatever you are most comfortable with. The domain and range, well, the domain, remember, is all possible x's. My equation tells me that I only have one possible x. And my graph is also not going left or right at all, so I know it's just a single number, -4. My range, however, since I have no limitations on my y, it goes down forever and up forever. So all possible y values, -infinity to infinity. sometimes you'll see relations listed in the form of a set of arrows between elements. This is the same thing as a list of ordered pairs. The place where the arrow starts is the x values. The place where the arrow ends are the y values. So we could rewrite this as a bunch of ordered pairs. They are letters, but they can still make up ordered pairs. Now, the way to tell whether or not a set of arrows is a function, do all my arrows start at a different place? No x value is mapped to two separate y values. Well, in this case, yes, every arrow starts at a different letter. So this is a function. The domain is all the x values, and that just means it is all the places where the arrows start. So E, D, C, and F. The range is all the y values, or all the letters at which the arrows end. U, W, V, and Z. We've already seen problems similar to this. The domain, again, is just the x values. This time we're back to dealing with numbers again. So the domain is all my x's, all my first numbers, 1, -2, 5, and then I have another 1, so I don't have to list it again. Since I listed 1 already once, I don't have to list it for a second time. My range is all the possible y values, 0, 3, -3, and 7. Is this particular relation a function? Well, I have two ordered pairs that have 1 as the x value, but they have different y values. So 1 is mapped to two separate numbers. That means it's not a function. We can't have two ordered pairs with the same x, but different y's. So this is not a function. For equations, when we're looking to see if they're functions, we want to be able to write y by itself. In other words, y equals f of x. The main thing that keeps us from doing that is when we have to take the square root to get rid of squared on y, or any even power of y, because when we take to get rid of an even power, we have to deal with the fact that positives or negatives fit in that. And so that would mean two separate x's would lead to, or two separate y's would give the same x, and that cannot happen in functions, as we know. So the main thing you're looking for when you're looking at equations to see if they can be written as a function is, do I have to take the square root of y to solve for y? If so, then it's not a function. The domain of functions is always negative infinity to infinity unless there is an x beneath the square root symbol, or there is an x beneath a fraction, because that gives us restrictions on what we can plug in for x. And I'll explain that in the lower two examples. You can see I already have an x under a square root for number 3 and an x under a fraction for number 4. So when we get to those, you'll see what I mean by this is causing us restrictions. But just know that in any other case, we're going to be looking at a negative infinity to infinity situation. For the first one, first we want to know, is it a function? And then if it is a function, I'm going to list the domain and range. If it's not a function, I'm done. So for this first example, I want to solve this for y in order to see if I can write it as a function. So the first thing I'd have to do is subtract x from both sides. So we have y squared equals negative 3 minus x. Now to get rid of the squared, I have to take the square root, but that was the one thing we said was a no on writing an equation as a function. So as soon as I do take this step, I have to go no further because this is not a function. So let's take a look at this other one. Number 2. I want to try to get the y by itself, so I'm going to add x to both sides. Y is now by itself. I didn't have to take a square root, so I know this is a function. Now that I know it's a function, I want to know the domain and range. Well, do I have x beneath the square root? No. Do I have x beneath a fraction? No. So my domain is negative infinity to infinity. And we can kind of see that from the fact that this is the graph of a line. And I will show you what I mean by that. I'm going to show you how to graph this using a graphing calculator if you have one. And what you'll have to when graphing is push the y equals button on the upper left hand side of the screen, and that takes us to where we can type in our equation. So now we're going to type in 7 plus x. The x button is next to the alpha, the green button just to the right of the green button is the x. That's where I'm getting the x from. I know you can't see the cursor that I'm using to push these, and I apologize for that. Hopefully that will be fixed next time. And then we hit the graph button in the upper right hand side, and it's going to graph it for us. Now my graph is zoomed in a little too much, so I'm going to hit zoom 6. If you can't see a graph when you're graphing it, you want to hit zoom 6 in order to go back to the standard screen size. So we see this as a line, and from the line we can see that it goes to the left forever, to the right forever. So that's where our domain is negative infinity to infinity. Similarly, we can see from the graph that, let's see if I can put this always on top so you can see it while I'm writing. I'm not seeing it on here, so we will, before I write it down, the line goes forever in a downward direction and forever in an upward direction. So we know then, since it's going forever in both directions, up and down, that the range is also negative infinity to infinity. Now, for the next two problems, they are already solved for y, so we know that they are functions. Just because y is by itself, I don't have to do any manipulation. So we're going to go straight into looking at the domain and range of these. We can graph them in the calculator, and that is a perfectly legitimate way of doing that. We go back to y equals, we push the clear button to clear out the old one. The square root button is this little, it's yellow and above the x squared, so we have to hit second to get to it, and then push the square root button. X minus 4 graph, and that's going to give us a little unique graph that looks like it has a starting point and goes to the right. So our educated guess here is that the domain is going to start at 4 and go to infinity. Now I already know that is correct because the reason square roots have restrictions is because I cannot take the square root of a negative number. If I bring the calculator back up and I make sure I'm in regular mode here, and I try to take the square root of a negative number, whatever it might be, I get a non-real answer. I cannot take the square root of a negative and get a real number answer. Now we will eventually get into the point in this course where we're talking about imaginary numbers, and that we'll deal with that when we get there. But as far as graphs and domain and range go, we're only looking for real answers, and the square root of a negative number does not give us a real answer. So the question becomes, what is the smallest number that I can take the square root of? Well, since I can't take the square root of negatives, the smallest number I could take the square root of is 0. And we know that the square root of 0 is 0. So the way I can find my starting point here is to take the part of the expression that is underneath the square root symbol, the x minus 4, and set it equal to 0. That will tell me what the smallest value is that I can plug into my function and still get a real answer. So to solve this, I'm just going to add 4 to both sides. And I get x equals 4. Now I know I can take the square root of positive numbers, that's fine. So I can go any number bigger than 4, I'm going to be good. But 4 is the bare minimum number I can plug into the square root. So, since 4 is the bare minimum I can plug in, my domain starts at 4 and goes upward to infinity. Now that I know the bare minimum for my domain, I can look back at the graph and see that if I plug in 4, I'm going to get 0 because my y value at that starting point, I've gone up or down none, so my y value is 0. Similarly, I can take this 4, plug it into my function. The square root of 4 minus 4 would be the square root of 0, which is 0. So since 4 was the minimum x value, I plug that in, I get my minimum y value. So my minimum y value is 0, and I can keep getting bigger, and the graph shows me that same thing. The graph goes upward forever. Fractions with variables on the bottom have their own set of problems, and we're going to clear out the old y equals 5. We're going to plug in our new function 5. The fraction bar is the same as the divide key, so we hit the divide key. Now I have more than one thing I'm dividing by. I'm dividing by x minus 3, so I have to put it in parentheses or my calculator will not graph it correctly. So notice 5 divided by parenthesis x minus 3 close parenthesis. We hit graph, and we see kind of a crazy thing going on there. The graph curves down, and then there's this big vertical line in the middle, and then the graph curves to the right. What that means is that vertical line, and we're going to discuss that in the future sections, but that vertical line does not literally exist on the graph. That is a line that divides two pieces of the graph. And it's called an asymptote, but we'll worry about that when we get to that section. But the thing you got to realize is what's causing that is I cannot divide by 0. That's the one thing that I'm restricted on in fractions. I cannot divide by 0. So what I have to do is take what is on the bottom of my fraction, set it equal to 0, so I know what x cannot be. So if I add 3 to both sides here, I find that if I had an x value of 3 and tried to plug it in here, I would get a 0 on the bottom of this fraction. I would have 5 over 0. Well, looking at the graph, I can see that my vertical line that divides the two pieces happens at x equals 1, 2, 3. So this is the one value x cannot be. So in order to write this in domain and range form, x can be every number from negative infinity to 3, but do not include 3. And then x can be every number from 3 onward. And I know that looks weird. This is called a union symbol, and it just connects two separate pieces of the graph. The first part of the graph, if I look back at it, goes from negative infinity until that vertical line at 3. So that's covered by the negative infinity to 3 piece. The second part of the graph is the curve in the upper right hand corner. That picks back up at 3 and goes onward forever. The range of this graph is negative infinity to 0 union 0 to infinity for the same reason. If I look at the graph, the left hand part never gets to 0, the right hand part never gets below 0, so 0 is the dividing factor of my range. And you won't see too many of these in this particular homework section, but we'll get to them more when we get to the rational functions homework later on in the semester. But it is important to kind of touch on what's happening there. When you're looking at domain and range of functions, you're looking at what possible x values do my graphs take if I were to graph them. That's why the graphing calculator is an important tool in this class, because we're going to be using it a lot to determine domain and range. We can get domain and range off of the graph, and I would just bear in mind that if you do not have a graphing calculator, it would be best to get one as we continue through the course. This last example in this section, if I don't pass it, we're going to come back to something a little easier. I already have y by itself, so I know this is a function. I need to know the domain and the range. Now I could graph it, and I will just for the purposes of this course. We're going to go to y equals clear 3x. This up arrow above the divide key is my power button. So 3x to the third minus 2x to the second plus 6x minus 1. Now before I hit graph, I'm going to scroll back up here and look at our instructions as far as this goes. Well, it's taking forever. The one thing we want to look for when we're looking to see if the negative infinity to infinity restriction on our domain is broken is whether or not x is beneath the square root or whether or not x is beneath a fraction. If I look at this function, I have no x's under square roots and I have no x's under fractions, so I should know right away that the domain, at least, if my pen will work, is negative infinity to infinity. Now the range may or may not be that, so that's why, again, it's a good idea to go ahead and graph this. In this case, my graph goes down forever, my graph goes up forever. And so I know that the range is also negative infinity to infinity.